Hello, everybody. Hope this finds you well. And I am quickly posting this review session. I will go on in 30 minutes later for a live review session. I am currently in a location with limited internet connectivity, so I hope this comes through in good quality. I also have my video off for that reason, and I will go on without video also for the live review session. So I'm just posting this to quick overview of what will be topic of the midterm exam that is due later this week. So I just quickly walk you through the slides, and I kind of just want to remind you of the bullet points that actually will be subject of this exam. So as you can recall from lecture 1, so we first talked about the different types of variables, where we basically have separated variables into numerical and categorical variables. It is to be understood what the differences between numerical and categoricals are, and the further substratifications of continuous and discrete. Just think of this basically in the format of the data that you have analyzed, where basically continuous variables, any possible variable that can take any possible value, whereas discrete is essentially some form of a count that you have as an example for that. You have with categorical, you basically have regular categorical that basically would be a nominal categorical variable that has, as the name implies, a name. Whereas ordinal is something that basically takes on some certain form of order. So for example, if you want to translate discrete variables that do have a count for an occurrence of a certain kind of categorical variables into a ranking, that would basically transform a discrete variable then into an ordinal variable. So please review this, and this needs to be understood for the midterm. Then we have further, we're talking about random assignment versus random sampling. So basically make sure that you review this part of your lectures that are being posted. You have the distinction between random sampling and random assignment, with the idea that you are able to have causal conclusion that can be generalized to a whole population, where essentially only random assignment can lead you to make causal inferences, even in the absence of random sampling. The problem that you have with random sampling in the absence of random assignment, as stated here, you will have generalizability, but you can essentially not make a causal conclusion, although you can generalize the findings and dynamics to your whole population, even after substratification. When you have no generalizability and you only have correlations without random assignment or random sampling, you're looking at a bad observational study. This being said, so essentially you need to understand your data. You need to understand the shape of a distribution. You have to understand the modes, which is kind of easy to grasp as a concept. So you're basically looking at most data, you're looking at unimodal data. And if you have several prominent peaks, you're basically looking at bimodal data or multimodal data. And if you have no apparent peaks, you talk about uniform data. You have to understand skewness, so data can be skewed. Right, skewness, when you have a tail shaping into the left end, you will basically have a left skewed distribution or negatively skewed distribution. Symmetric would be a somewhat symmetric shape. It's not exact science to determine the skewnesses, but to some extent, this will essentially lead you to judge and to describe the shape of your distribution. This further can be read from a so-called box whisker plot. Keep in mind two things. So first of all, you do have here the median, you do have Q1 and Q3, but essentially the box captures 50%, so the middle 50% of data. Everything above that is essentially to be considered the so-called whisker, where basically you have the upper end of the whisker is the Q3 multiplied, now it's Q3 plus 1.5 times the interquartile range, which is Q3 minus Q1. So 1.5 times this IQR essentially gives you the value of the maximum whisker, and in the same fashion you calculate the lower whisker, and everything that exceeds either the upper or the lower whisker essentially is considered an outlier in a box whisker plot, which essentially also then leads you to allow for you to judge the distribution of the skewness. So if you have more outliers to the upper end, you're looking at, according to the Y scale, to a positively skewed distribution. The normal distribution needs to be understood. You have a unimodal and symmetric bell-shaped curve in a normal distribution. The notation is that the x as a function of a normal distribution where n is being distributed with a sigma of the standard deviation. So the standard deviation denoted here sigma. This is a population because you have a mu and you have a sigma. Both mu and sigma are Greek levels that basically indicate they are derived from a population, whereas an x bar and an SD on S will basically denote it comes from a sample. So you have population parameters as stated here. Keep in mind when you distinguish those two. You further have done the standardization. The standardization is done with set scores. Set scores are essentially standardized scores where you standardize each individual point as the difference expressed in the number of standard deviations, which means essentially you're calculating the individual x minus your mean, and you divide it by sigma, which gives you the number of sigmas this individual point is distant from the mean. So you essentially have as a standard deviation of 1 is considered to be 1 standard deviation away from the mean. -1 would be less 1 standard deviation from the mean. So this is important to keep in mind, that it needs to be understood what this expresses. Essentially here you see this being brought into action. You have a normal distribution with heart rates and beats per minute. This essentially is around a mean of 60 with a standard deviation here, notably of 10, which essentially gets you to that point of 10, which is 60 plus 10 is essentially 0 plus 1. So it's 1 standard deviation away, that would be 70 beats per minute. If you would try to translate this now on a different data set, and you want to calculate now certain values, that you have the calculation in your respective lecture notes, you essentially can do the same thing. You have, if blood pressure is known to be normally distributed with mu around 120 and the sigma of 20, you have a sigma plus 1 at 140 and the sigma of -1. And a set of -1 as 100. This exercise can essentially be done by using the norm dist function as you have done in your exercises. So you enter the respective value. So you have as the x of interest, you have 100. You can then use 100. You enter next a mean of 120, the standard deviation of 20. you have a cumulative as equals true, that essentially will calculate you everything less than 100 as being the region of interest. This will be done by under the assumption that or the entire area under the curve, under this normal distribution curve, is considered to be 1. Everything to the left of this point is considered to be that fraction of interest. So everything less than this x of interest will be expressed with the norm dist function if you set cumulative as true. If you want to know everything that is above that value, you're doing the opposite. You're basically calculating 1 minus that formula or that value that essentially will give you everything greater than this value. Good. So now the question is this is what I just alluded to. So essentially you have 1 minus that value will get you to all the others that have a historic blood pressure greater than 100. I think these are simple exercises that we have done quite extensively in earlier lectures. So the same exercise here with 133. So you basically have 1 minus p of x minus x smaller than 133. So you have the same exercise here. You do 1 minus norm dist is 133, 120, standard deviation of 20. You do true for cumulative, and basically gets you to 0.26 as your value of interest. Just make sure, and I highly recommend, in case there's an exercise, always map it out and kind of graph it out on a piece of paper. The same exercise exists here, where basically you have to assume that everything to the left is being quantified with the norm dist. So if you calculate 1 minus this, it gets you everything greater than this. If you calculate 1 minus this, gets you everything greater than this. So if you have 1 minus this and minus this, the result is going to be this. So this is essentially how you will calculate the in-between examples. And you will find this in the respective lecture notes. So finding cutoff points is essentially the same kind of exercise where you need to understand how to rearrange these formulae. So if you have a formula of z equals x minus mu divided by sigma, and you divide by the standard deviation, if you want to rearrange that and you actually want to find the respective points, you just have to calculate x equals mu plus z multiplied by sigma. That will give you the respective numerical value. Same exercise here. You're interested in something like 8%, 3% of your population. This basically will allow you to calculate the observed x minus the mean divided by the standard deviation. Gets you essentially to calculate x that is considered an threshold below which you have 3% of your population. So I encourage you to calculate all these examples and to also go back to your exercises that we have done in the respective lectures. So here we have the 68, 95, 99.7 rule. So you have 68% fall within 1 standard deviation of the mean. This is this range. 95 fall into, it's not strictly 95, it's an empirical rule. So basically 2 standard deviation capture 95 of the data, and 99% captures 3 standard deviation of the error. Contingency tables are a way to depict counts and to give an overview of distribution within certain nominal categories. You basically, it's a summarization table that allows you to do easily calculations. With a binomial distribution, you basically have a way to calculate the probability of success for each individual mutual exclusive event counts as one probability entry. the probability. 1 minus p would be the probability of failure, and represents the number of independent trials, and k represents the number of successes. So essentially, this is a formula to calculate this, which will then be utilized later on when we are getting to that examples. Okay, you can also utilize these formula to essentially calculate. So you are using a binomial distribution where basically your mu sample, and you're assuming here that you randomly have drawn samples and you get estimates of that actual percentage prevalence in your sample that will be a representation of the prevalence in the population. So basically mu equals n multiplied by the p, which is essentially that true mean. The standard deviation here is calculated as sigma equals the square root of n, which is the n of your sample, multiplied by the p, multiplied by 1 minus p. So it's a success probability multiplied by the failure probability multiplied by your sample size. That essentially gets you to calculate a sigma. And from there, you can essentially go towards calculation of standard error of the mean, as we'll see later. So this distribution essentially gets you to a real prevalence, and then essentially an estimate of what prevalence can be considered to be different with a given sample size from the population prevalence. And this will be part of exercises you may be facing. So please go back to the respective exercises to make sure that you are clear on how these are being conducted. There are more practices. So you basically you're using then in bring this into practice, you're using a normal approximation. We basically assume that if you have random samples that you're drawing from a population of a certain size, these will basically distribute with a certain standard deviation that can be calculated here as n multiplied by success probability multiplied by failure probability, gets your standard deviation, and then you calculate around that the standard error of the mean as being seen in the following. So you essentially have these repeated samples. This essentially gets you to then calculate your standard error of the mean. That essentially will allow you to do hypothesis testing, because you essentially are calculating now. And this is an approximation. This can be here, can be seen here. So the PQ, where P is the probability of success, Q is the probability of failure divided by the sample size and the square root, essentially can be used for hypothesis testing, as we will see later on. Both for continuous data as well as for proportional data, you can employ the calculation of the confidence interval by calculating the X bar, or the prevalence in that, or the proportion in that context of the binomial distribution via normal approximation. You can calculate X bar plus minus that's set critically, depending on what critical value you're interested in, whether it's 5%, 10%, or 1%. You're taking the respective set score of interest multiplied by the standard error of the mean. This will allow you to quantify the margin of error and the confidence interval. So the reason why you're doing that is because you can assume then there's a 95% confidence interval that if you draw 100 samples and you have a significant difference, that less than 5 of your 100 samples will be significantly different. So essentially you get 95% confidence that your interval, your confidence interval, contains the true population mean. This is also then leading into hypothesis testing. We actually do significance testing. So basically, we are first formulating a null and alternative hypothesis, where the null hypothesis indicates no significant difference between both sample and population mean. We are then evaluating the correct test statistics, and we're converting the test statistics into a p-value, where essentially we are assuming that the difference after standardization into the standard error of the mean, assuming that that standard error of the mean is relating to population standard deviation, for example, on a set test, does essentially allow for standardization, and the standardization indicates with what probability that sample is actually coming from the same population, or is essentially significantly different from the population mean. Basically, you determine a significance level alpha, and you decide based on that decided alpha whether the p-value that you're deriving from your calculation is essentially smaller than the respective alpha, where the alpha is essentially the type 1 error that you're willing to accept, where the type 1 error is that you're rejecting an null hypothesis that you actually should not have rejected. So the null hypothesis is the claim of no difference, the alternative hypothesis is a claim of difference, and you're basically seeking evidence against the claim of the null hypothesis, a way of bolstering or supporting or corroborating the alternative hypothesis. So these are the decision errors. So basically, you have a type 1 error, which is a type 1 error where you reject the null hypothesis when null hypothesis is true. So essentially, null type 1 errors often occurring when you do subsetting, or you do like removal of outliers that you shouldn't have removed. But there are various reasons leading to a type 1 error, where a type 2 error is essentially failing to reject the null hypothesis, and the null hypothesis actually, when the alternative hypothesis is actually true, and you're wrongly accepting the null hypothesis. This is essentially mostly found with wrong power calculations, for example, in randomized controlled trials, which were studied with a certain sample size based on the power calculation. If that was done wrongly and the power calculation resulted in wrong sample size estimation, you essentially will end up with a potential type 2 error. So type 1 error essentially is based on that alpha. That alpha needs to be chosen with whatever alpha you're comfortable with in that research question. So essentially, the different levels to that. Type 2 error is essentially also leading to an estimate of the power. So 1 minus this type 2 error is essentially the statistical power, and you can set this to either 80 or 90 for the design of a study. So now we're getting to the actual methodologies of hypothesis testing. So we have here one sample t-test, we have hypothesis to be put forward. It is important that you understand between two-sided, left-sided, and right-sided, one-sided tests, which essentially follow the same outline, but you need to understand in which direction you're posing your question. And it also depends which one you actually think your mean is being shifted to. So if it's smaller, then your null hypothesis is essentially that mu is greater than mu0. And the alternative hypothesis, as stated here, that your mu is smaller as your mu0. So it's important to understand this, that left-sided is in that context essentially the alternative hypothesis points toward a sample being assumed to be smaller under the alternative hypothesis. So then essentially you just move forward, you calculate just with this one-sided set test, you're calculating x bar minus your mu0 divided by the standard error of the mean which is calculated here, standard deviation divided by square root of the n, with a degree of freedom of n minus 1. So this is a distinction of your set statistic, where the set statistic is the degrees of freedom that the sample size are equal. Here this is different because we are meaning with the t-statistic to approximate the set statistic and to kind of approximate the normal distribution. So keep in mind, and please review that essentially. Lecture. Confidence intervals are essentially point estimates, where essentially are being calculated in the same fashion as the set value. Paired samples are essentially a chronological order of samples that are being drawn. It's a before and after situation where you basically have matched pairs or dependent samples, which are in contrast with independent samples. So please understand the difference, that it's two different groups. So if you have before and after, there's some relationship between the samples before and after. Don't use an independent sample, but use a paired sample t-test. If you have two independent groups, always think of an independent samples t-test. Significant tests are essentially now towards mean differences. So essentially, you calculate the difference between before and after. And this difference is you basically comparing to a difference of 0. So that means that essentially you're assuming there's no difference between before and after. And you're calculating a difference between before and after. And this is what you hear standardizing or testing against the difference of 0, which essentially will then give you a certain t-statistic, and this t-statistic you will read from t-squared table. T-statistic, we talked about this. Independent samples are basically compared to each other. It's two separate groups with no matching or pairing. The calculation is done with a so-called pool standard error, which essentially allows you to calculate x1 minus x bar 1 minus x bar 2. Divided by that standard error basically allows you to get a t-statistic for an independent sample t-test. You get degrees of freedom. By that, you can allow yourself to calculate the p-value and to do hypothesis testing. So here's an overview of those formula. It's important to keep in mind and to help yourself to kind of be able to distinguish between those parts. Recap, sample sizes and power are basically interrelated. It's important to keep in mind that you have understanding of these. So basically the power increases by increases in the effect size, by increase in the sample size, and by decreases in the variability, whereas the decrease in the variability is obviously not modifiable because you're assuming that based on previous literature. So you do with the effect size. So the only thing you can really alter here is the sample size of the group. So you increase the sample size, you decrease the standard deviation, not possible. You increase the alpha, which is also not advisable. We consider large effect size. It's also not always possible because that would mean to intensify your intervention. The cross tabulations, please understand risks, which are basically calculated as A1 divided by N1, which is in the group, the actual risk of a success. Do the same for your N2. That essentially allows you to compare those two. Risk difference and relative risk are two different markers. One is a difference, the other one is a ratio. The ratio has a different interpretation, which we've discussed in the respective lecture. Equally, the odds ratio and we get later to the risk ratio are two different relative measures of association, which need to be understood. Everything greater than 1, depending on the reference group, everything greater than 1 indicates a greater risk in the actual group in the numerator, as compared to the reference group in the denominator. One sample test can here be calculated in the form of quantification of standard error of the mean. The standard error of the mean allows you to calculate the confidence interval. Two sample t-tests, essentially equally, you can calculate here probabilities. Chi-squared, understand chi-squared is observed minus expected, which essentially gets you to a chi-squared statistics, which you're comparing against the positively skewed uniform distribution, where the degrees of freedom are the row minus 1 and the column minus 1, and essentially leads you to estimate a p-value based on the chi-squared table. Please understand correlation coefficient. Understand that -1 and +1 are basically the maxima. That means it can be either be inverse correlation or positive correlation. The absolute value indicates the strength of the relationship. That means like -1 and +1 are equally strong relationships. It's just the direction changes. Then we have regression analysis, which basically is a functional relationship between independent variable and explanatory variable x, which essentially is either simple linear regression or multiple linear regression. These scatter plots and functions are usually determined by the least square method, which is essentially equal to finding a line that best describes this association. Keep in mind that you understand this relationship where you basically have the dependent variable as a function of the beta 0 plus a beta 1 multiplied by that x, which is your independent variable plus the residual error. And if you go into multiple regression, it looks in the same fashion, and you can add additional coefficients in this equation, which you see here, for example. Let's see this. So what's also important to keep in mind that the correlation coefficient gives you with the standard deviations y and standard deviation x a means to kind of estimate your b1, which is essentially your slope. B0 is y bar minus b1x minus x bar, which gives you another indicator of that regression is the intercept. You have prediction models and explanatory models where you identify groups at risk, you identify possibly contributing coefficients, and in an explanatory model, you actually try to assess causality, and it's based on a theory. So for that, you also build directed acyclic graphs, which will be part of applied bias, that's one. But you still suffer from confounding and selection bias. You're basically testing the hypothesis that your fit line is basically a flat line according to the mean of y. So basically you're testing that your model or your correlation is actually stronger than just the mean of y. The test statistic is here. B minus beta equal divided by the standard error is actually B over standard error is actually smaller than 0.05. You can extend this to two or more predictive variables, and by that you essentially look at multivariable regression. You can do this to account for several explanatory variables. It accounts for confounding. And you can employ effect modification and detect effect modification. It can be easily done with all kinds of softwares nowadays, and you've got to be careful about sample size. The relationship between sample size and explanatory variables should be 10 times the number of variables should be the sample size. Confounding is here related to exposure risk factors related to the outcome. not in the causal pathway, which is important to keep in mind. So you need to distinguish between confounders, mediators, effect modifiers, and statistical colliders, which will be subject of future educations for you. Logistic regression is basically a linear regression model that is being extrapolated to only distribute between an outcome of 1 and 0. So you basically you shape a logarithmic function between these two numbers to essentially be able to extrapolate it to a linear increase towards 0 or towards infinity. And by that, you essentially get estimates of the so-called log odds that after rearrangement and retransformation into an exponentiated value, exponentiated by Euler's number, basically will allow you to estimate or to express the so-called odds ratio based on this relationship between that linear shaped function between 1 and 0, and to allow us to kind of extrapolate it to the odds ratio. More about that in the lecture. Okay, so that was a quick review of what we have discussed this semester. If any questions, let me know. Utilize the discussion board. I will try to make sure to always check it by the end of the day. And I will also go online now on the review session, and I will catch you there who went online. Otherwise, good luck on the midterm exam. We'll talk soon. Bye-bye.